Welcome to part 2 of the video on limits on infinity. In the second part, we're going to solve more examples of limits on infinity. We're going to solve an example that can be solved in two ways. And then a very interesting example is the limit of an infinite sum. So let's begin with this example here. We have the limit as x approaches infinity of x plus 1 over x. So let's remember the basic technique for solving limits at infinity. The first step is to find the greatest exponent in the expression. In this case, it is 1 because we only have x, we don't have x squared, so the greatest exponent is 1. The second step is to divide everything by x. If we do that, we divide each term by x, we get this, and now we can cancel the x here, cancel the x, and we get the expression 1 plus 1 over x. And now it is easy to calculate this limit because 1 over x approaches 0 because x approaches infinity. So this limit equals 1, and that's the answer. Now there is an alternative method for solving this limit. We can directly write this algebraic expression as the sum of these two terms, like this. This is just sum of fractions. And we can cancel the x, and we get the same expression that we got before. And we can this limit equals 1. So you can see that you can solve this limit in these two ways. And this shows that for solving limits, you can use any algebraic trick that you know how to use, alright? It is very similar to solving problems in algebra. You can do all the tricks that you know. Now, let's try to solve this very different problem. Here we have a sum in the numerator, and we have n approaching infinity. As n approaches infinity, we see that the number of terms in the numerator increases with n. So as n approaches infinity, this becomes an infinite sum. This is a very interesting problem. And we have this sum divided by n squared. And we want to know what this approaches. And we can know that the numerator is an arithmetic progression. It is a special type of sum. So there is a way to find a formula for the sum of an arithmetic progression. We can write the sum like this, or we can write it like this. Here we only rearrange the order of the terms. Here we start with 1, and we here start with n. And we go decreasing from n to 1. We just rearrange the terms like this, and we can take the sum of these two equations, and we get that this will equal, we're going to sum term by term. Here we have n plus 1. In the second term we have n minus 1 plus 2. In the third term we have n minus 2 plus 3. And we continue like that, and the last term will be n plus 1. And we see that each of these terms is also an n plus 1. So what we really have here is n terms that all equal n plus 1. So we can write this as n times n plus 1. And on the other side of the equation we have 2Sn. And we can solve for Sn, that is the sum, and you get this closed formula for the sum of an arithmetic progression like this. So what we are going to do now is to replace that formula in our limit. We can replace this sum with this formula, and now this limit is much easier to solve. We can transform this into this, and now we can perform this product here, we get n squared plus n. And now we're going to apply the basic technique. We must divide by n to the greatest exponent. Here we have n squared. So we divide each term by n squared. We do that here, we divided each term by n squared. Here we can cancel the n squared. Here we can cancel n. Here we can cancel n squared. We get this expression. And now we know that 1 over n will approach 0. So the limit is 1/2. That's the answer. So this was a pretty interesting problem. It shows that, well, it shows again that you can use any algebraic technique for solving limits. For example, taking the sum of an arithmetic regression. So that's all for now. Thank you for watching and see you next time.